Hi there, my name is Vince Haralabidis, and in this video, which will be the first video in our series of videos regarding calculus, we will try to have a short, concise introduction to calculus. And more precisely, we will introduce two fundamental concepts around calculus. The one of the rate of change of a function over an interval, and the second one, and more key one with regards to calculus, the one that refers to the instantaneous rate of change at a point of a graph. Now, let's begin with a small inquiry. Let's write that here, inquiry. And I will now draw two graphs of two functions, f and g. This is the x-axis and this is the y-axis. And that one would be this. This is point with coordinates a, f of a, and here with coordinates b, f of b. And at the same time, this, the next one, is a graph of another function g this time, where here we have a g of a, and here we have b and g of b. Now, in both of them, I can see that the values from when x is a to where x is b increase in both of them, both in the top graph, which refers to the graph of f, and both to the bottom graph, which refers to the graph of a second function g. We can see that f of a is smaller than f of b, and at the same time, g of a is smaller than g of b. But the question now is, in which one, however, is this increase the most? Obviously, again, we can easily see that in front of us, that in graph of the function f, which is the top graph, there is a bigger distance from the values f of b to f of a. We can see that here, the values of f had to cover all this distance, while in the graph of g, they had to cover simply that. So yes, we would answer to this question that in f, it seems that the increase was bigger. However, is there a way to actually measure that difference, measure that increase? Yes, the answer to that would be yes. We can do that through what we know as average rate of change. From now on, we will refer to that as AROC. And we can give the following definition. The average rate of change of a function f over an interval a, b is a measurement that shows how much a function's values change, because they cannot just increase, they can as well decrease. So how much a function's values change per unit on average over an interval. That's exactly the interpretation of the average rate of change. It can be calculated by the formula. Average rate of change on AB is f of B minus f of A over B minus A. So once again, the key points are that the average rate of change is a measurement that shows how much a function's values change per unit over an interval, and secondly, it can be given through this, through this formula. For example, example number 1, find the average rate of change of f of x equals x squared plus 1 over the interval 1, 2. To do that, all that I have to do is just apply the formula. So average rate of change would be equal to f of 2 minus f of 1 over 2 minus 1, which means I can go somewhere in a corner and calculate these values separately. F of 2 is 2 squared plus 1, which is 5, and f of 1 is 1 squared plus 1, which is 2. So I'll return back to the formula, and I should write 5 minus 2 over 1, which is equal to 3 over 1, which is equal to 3, which means that over this interval from 1 to 2, the function's values change per 3 per units of inputs at average. Now, a second way, we might be given just a graph. Find average rate of change of f over 2 and 6. And this might as well be escorted by that graph, x and y, and we might have had this, where this is 2, this is, let's say, 6, the value here was 3, the value here was 5. So once again, average rate of change, the only difference here is that in order to calculate the values, we would have used the graph and not the functions notation. The average rate of change, however, would have been f of 6 minus f of 2 over 6 minus 2. F of 6 we can see from the graph that is equal to 5. F of 3 is equal to 3. F of 2 is equal to 3. 6 minus 2 is 4. So that would have been 2 over 4 equals 1/2, which means that as we progress from x equals 2 to y to x equals 6, the function's values, that is the y's, increase by 1/2 per moving unit. Every time x increases by 1, the y over, on average, on this interval, the y is expected to increase by 1/2. A note here that we should keep in mind is the geometrical interpretation of the average rate of change. Geometrical interpretation of average rate of change. Look at how we defined the average rate of change on the interval AB. We said that this can be given by f of B minus f of A over B minus A. Now, does this formula remind us of anything? It should, because I assume that most of you have already seen that more than one times. We have, or you should have seen that by now, when working with straight lines. If you remember back then, we've said that if we are given 2 points, x1, y1, and x2, y2, the slope of the line passing through these can be given as the y2 minus y1, the difference in y values, over the x2 minus x1. Can I combine these two? Of course I can. Look at the graph. Assume that we have the graph of that function f. And assume as well that this is the point with coordinates a and f of a, and that this is the point with coordinates b and f of b. We have 2 points. If we apply that formula, we will see that f of b minus f of a over b minus a, which is the average rate of change, at the same time, it's the slope of the line connecting points with coordinates a, f of a, and b, f of b. So, in our case, it would have been the slope of that line. So, the average rate of change over an interval AB actually geometrically demonstrates the slope of the line connecting these two endpoints. And by now, we should keep these key parts. Average rate of change, it's something, it's a measurement, it's a number that shows how much the y values of a function change per average on a given interval every time the x units increase by 1. In order to calculate that, we have a certain formula, and through that formula, we actually understood the geometrical interpretation of that, which is that it refers to the slope of the line connecting these two endpoints. Now, let's take it one step further, and let's do this question on our mind. We saw that there can actually be an average rate of change between 2 points, A and B. Can we find an average rate of change at a specific point at x equals 2? Or is it that we always need to have 2 different points? Let's see about that. First of all, the answer is yes, we can do that. And basically, the reason why we're doing this introductory video is that this concept, the concept of having a rate of change at a specific point, which is, by the way, called instantaneous rate of change, is the key element of calculus. Through calculus, we will see that this can be achieved by another function which is called derivative of f. But for now, conceptually, we should know that the average rate, the instantaneous rate of change, that I stands for instantaneous rate of change, shows how fast a function is changing exactly at that point. Geometrically, we've said that with regards to the average rate of change, we should think of that as the slope of the line connecting these two endpoints. Now, for the instantaneous rate of change, geometrically, we should do the following. Imagine zooming in the graph that much so that at this specific point, it looks like a line. Then the instantaneous rate of change will be the slope of that line. If I try to do that here, if we have, let's say, the graph of f, and I want to calculate the instantaneous rate of change as x0, I should think of that as zooming in that much so that at this point, the graph doesn't look like a curvy one, but it looks more like a line. The slope of that line would have been the instantaneous rate of change. So, in other words, you can think of that as the slope of the tangent at that point. So, instantaneous rate of change at x0 can also be seen as the slope of tangent to the graph at that point. To understand its value, we should do the following example. Let's say that we want to find the instantaneous rate of change of f of x equals x plus 1 at x equals 1. Since we only have a formula for the average rate of change, I should try to approach the instantaneous rate of change by creating an interval so small that would be thought as just a single point. What do I mean about that? I would start by creating the average rate of change from 1 to 1.1. Based on our formula, this stands for f of 1.1 minus f of 1 over 1.1 minus 1. The f of 1.1 is obviously equal to 2.1 minus 2 over 0.1, which is 2.1 minus 2, it's 0.1 over 0.1 is 1. Let's make it even smaller, 1.1.01. The average rate of change on that interval would have been 1, f of 1,01 minus f of 1 over 1,01 minus 1, which means f of 1,01 would have been 2,01 minus 1 over 1 over 2, sorry. 1, minus 1 minus 1 would have been 0,01. So that would have been 0,01 over 0,01. It's still 1. Let's make it even smaller. 1,001. The same here again. We would have ended up at 1. So regardless of how small that interval is really, so even if we approach that with an interval of 1,1.0000001, in the end, by following the exact same substitutions, the average rate of change would still have been 1. And that is exactly the concept of the instantaneous rate of change. Look, here, simply because the original function f of x was a line, and in a line we have a constant rate of change, we were able to find the instantaneous rate of change right from the very beginning. But if it was another graph, a random function, and we would have followed the same process of minimizing the interval, we would have seen that the smaller the interval would be, the closest, not the most, the closest we would approach to a certain number. That certain number would be the one that we would have called instantaneous rate of change. That's all. Keep in mind that everything around calculus is created on that key idea. The idea of calculating the instantaneous rate of change of a function at a certain point. Again, to recap, what is the average rate of change? The average rate of change is a measurement that shows how fast the values of y of a function change. They can either increase or decrease. Change per average, per unit within a specific interval. Average rate of change of 3 in interval 2,6 means that as we go from 2 to 6 on the graph's units increase on average by 3 units every single time. For every increase in the x values, the y's should be expected to increase on an average by 3 units and so on. So that's the idea of the average rate of change. The geometrical interpretation of it is that it's the slope between the two endpoints. And then we have the instantaneous rate of change, which is basically the idea to see how fast the values of a function change at a specific point. Its geometrical interpretation, which remains yet to be clearly seen in one of the following videos, is the slope of the tangent to the graph of that function at that specific point. And that would be all. I hope I made some things clear enough. In case you still have some questions, in case you still want to clarify anything, please feel free to leave your comment below the video. As always, thank you for your time.